And we want to talk about kind of linking together some of these properties of liquids, specifically vapor pressure and boiling point, and we'll see how we can apply this insight into general discussion of phase changes. So we know that we have these different phases of matter, solid, liquid, gas, and we talked about some general ideas. Going from the ordered phases, say solid to liquid to gas, is always an endothermic process. Energy has to go into the substance because the molecules are moving more. Whereas going the opposite direction, gas to liquid to solid is always exothermic. So when we do those processes, we would release heat. So we put heat in to melt, to boil, and then the fancy words for those are fusion, vaporization, and sublimation. So there are technical, fusion is the technical term for melting, vaporization is the technical term for boiling, sublimation is gas straight to solid. We do have condensation, kind of the words the other direction, condensation and freezing we're used to, and deposition is gas into solid. And we are always cooling those things down. Heat is coming out, heat would be going into the surroundings. And so we want to get into talking about phase changes, and we already have some kind of general guidance for them, and so of how phase changes work. We want to look at some other insight into how phase changes work, what some of these energies associated with them are. So one of the things we want to return to is vapor pressure. And we kind of touched very end the last time about the idea that as you increase temperature or you change temperature, you're going to affect liquid properties. And as you increase the temperature of any liquid, you are going to increase the vapor pressure above that liquid, because increasing temperature always leads to molecules moving faster. Faster molecules in this case means those liquid molecules are kind of jostling around, and they're going to be able to escape out into the vapor phase. And so the vapor pressure always increases with temperature. So this is a graph of water. You can see from 0 to 100 where liquid is present under ambient conditions, how the vapor pressure changes. At very low temperatures, the vapor pressure is really low. It increases exponentially. And so at really high temperatures, the vapor pressure starts to grow really quickly and keeps going up and up and up. And if we kind of look at this graph, there are some relevant points. This right here would be ambient pressure of air at sea level. So this is in millibar. So ambient temperature is about 1 bar, which would be, it's just over 1,000 millibars. This is 1 atmosphere of pressure unit is ambient pressure at sea level. And if you'll note where that line crosses is 100 degrees Celsius, which is the temperature where water boils. This is not accidental. So when we think about making vapor pressure, as our vapor pressure is increasing higher and higher and higher, we would think that there are more and more gas molecules in the gas phase, leaving the liquid and going into the gas phase. Eventually, there are so many molecules in the gas phase that it stops being a vapor and we just have boiling. So the reason why liquids boil is when their vapor pressure equals the pressure of the surrounding air. So basically you can think about that the pressure, one of the things keeping air pressure, right, is pushing on the surface of the liquid. And so that's actually kind of keeping molecules in the liquid phase. Once the vapor pressure becomes so high that it equals that sort of ambient pressure, the pressure of the air pressing down on the surface, then the molecules from the liquid can just escape. There's nothing holding them in the liquid, and they would just be escaping out into the gas phase, and you get boiling. And so if we define a standard pressure, so air at 25 degrees Celsius at sea level, that is 1 atmosphere, we call that the normal boiling point. So when we hit 1 atmosphere of vapor pressure, we call that the normal boiling point. And so down in the greater Houston area or in most coastal cities, that is where the temperature of water boils. But that's only true at 1 atmosphere. If you change the ambient pressure of air, the observed temperature of boiling is going to change. So the main way that we see that is changing elevation. So here in the United States, if you go to more mountainous cities, for example, Salt Lake or Denver, as you go up to those elevations, up into the Rockies, you're going to get a decrease in the boiling point of water. The observed boiling point is at 95 degrees Celsius in those cases. And so that the water really is at a lower temperature because the environment, the surroundings. We can see that this phase change, boiling, that we're seeing is not just dependent on the water itself, but also what is around the water, right? How are the conditions of the water affecting it? If you keep going up, La Paz is one of the highest elevation populous cities in Bolivia. You get down to 91. Mount Everest, your boiling point would drop down to 76. If you went to like space, it would get even lower. Because there's no pressure, there's really nothing holding the air in, or the molecules in the water, and so they would just be able to, would boil, seemingly boil at low temperature. One of the important things to note is this water is colder, and so even though it looks like it's boiling, it still is boiling, it's just not as hot. So you'll see some indications, some recipes that deal with boiling will say that if you're at like a high elevation, if you live in Denver or Salt Lake, you should boil it for a little bit longer. You should cook something for longer because the water literally is less hot. If you lived in like La Paz, you would want to wait even longer because the water is less hot. And so if you went higher and higher elevation, you could like stick your hand in boiling water because boiling doesn't indicate anything with temperature. It only indicates where the vapor pressure of that liquid equals ambient pressure. And so if the ambient pressure is lower, that temperature is lower. We can also see when we relate this idea of vapor pressure, we know that molecules with weaker intermolecular forces, for example, acetone in the red curve, we know that it always has a higher vapor pressure than something with strong intermolecular forces, for example, water with the blue curve. Acetone is only dipole-dipole, so it has weaker intermolecular forces. Those molecules can escape from the liquid more readily and go out into the vapor phase. And so as a result, at every single temperature, acetone has a higher vapor pressure than water. As a result, its boiling point is still determined by when the vapor pressure equals ambient pressure. And so that's why it boils at a lower temperature. So we learned about that idea, this sort of trend, and we can understand a little bit more. It's all about this vapor pressure is determining when boiling happens. And it's all based around that. We can also take this insight. So this is still the curve of the vapor pressure of water versus temperature. So you can see how does the vapor pressure of water change versus temperature. You'll note I've changed the curve. We're now dealing with Fahrenheit because we're going to be talking about human temperatures. And so when we look at this graph, it looks like a single line, a single curve relating air temperature to pressure of water and air. And what this graph tells us is that if you have, like a glass of water, if you have a glass of water and you put that in there, you put water in there, woof, you put water in there, what sort of pressure of air molecules there will be above it? What number of air molecules, okay, is going to be above it? And that's what that line tells you, okay? The other way we could interpret this, what this tells you is that this line is the maximum partial pressure of water in air for a given temperature. So this region up here is not possible. For those temperatures, any point above the line is impossible. So if it is 60 degrees Fahrenheit, there cannot be more water in the air than, what's that, 0.015 atmospheres of water. So 1 atmosphere would be the air is, the air, all of the air is water. And so here we'd be looking at something like, say, a 1.5% of water, of molecules in the air are water. And it is impossible to have that because if you had more than that, it would just become liquid water. That green, that zone, this shaded out zone is impossible because if you prepared a gas with that much water in it, in the gas phase, at that temperature, it would collect out as liquid water. It would collapse out as liquid water. So instead, air exists somewhere over here. So that dot right there is representative of what it tends to feel like in, say, Houston in the summer, where you're in, say, the air temperatures in the low to mid 90s and a relatively high humidity. That humidity, about 2.5% of molecules in the air are water molecules. And so that amount of water in the air, the partial pressure of water in the air, it's below the line, so it's possible. And so, but that stays fairly constant. The number of water molecules in the air doesn't really change with the day. What does change is the temperature. Especially at night, we cool down here, right? So the air cools down. Eventually, you're going to hit that line. As the air cools down, you will hit a temperature where you have reached the maximum vapor pressure of water in the air. And what happens is you form liquid water. That's why we get dew here in the mornings. Right? That's why there's dew all over the place. That water was in the air. When the air is hot during the day, all of those molecules can be supported as gas phase molecules, humidity. But at night, when the air cools down, it cannot happen. Right? You can't get that sort of you can't have those molecules be in the air as gas molecules. They collapse out and they form liquid water. That's where dew comes from. Fog is a similar idea. That's why fog forms. It's the exact same idea. That is what 100% humidity looks like. Right? So one of my pet peeves during the day here, it is not 100% humidity because there's not dew on the ground. Dew on the ground or fog in the air is what 100% humidity looks like. The air, as there are as many water molecules as possible in the air, they have started to form liquid because there's too many of them. One of the implications of this, gas to liquid is an exothermic process. And so this is why at night here, it doesn't cool down because of humidity. All of that water that's in the air is becoming, that's gas in the air, is becoming a liquid. That releases heat that warms up the air at night. So humid places don't cool off. This is why deserts do cool down. You'll learn about, people always reference like cloud cover, and that is an important aspect, but a much bigger factor is the fact that air in deserts is very dry. So it's like, say, here, very low humidity. Even if it's the same heat during the day, you can cool all the way down, and there's no creation of water that starts to release heat to offset that. So if you look at the dew point, you can see that is our dew points are pretty high here. It cannot get colder than the dew point because you just start making water and that releases heat, keeps the air warm.
There we go, first video down. So we'll be on our kind of normal full week schedule. We will have 2 participations for both sets of videos this week. This set of videos is just this first set, finishing up chapter 10 here. This one's due Tuesday, so this participation is due Tuesday. Participation 118 is what we're looking for here. Then this first set of videos, at the end of chapter 10, will also be covered on the homework due Wednesday. And then also Wednesday, you'll come in to do the lab. So with this lab, we'll have the full kind of all the parts of the assignment you need to do. So you want to take care of the pre-lab assignment, you want to do the technique, watch the video, do the little assignment, and fill out part of the notebook all before coming to class on Wednesday. So all of that is due before coming to class on Wednesday at 1 p.m. Post-lab, you do afterwards. If you have any questions about how to do anything, I know this is all still new, let me know. Happy to answer, get all of that sorted out. But otherwise, welcome to the beginning of the end of chapter 10. See you in the next video.